Look at this system. It is a dense, intricate maze of pathways and components. In engineering, a network like this is often designated as a black box, an assembly where the internal currents and voltages are unknown until they are analytically derived. Predicting the behavior of any electrical circuit requires first defining the foundational boundary conditions of its individual components. To achieve this, every component is strictly classified across two independent dimensions. The first dimension is thermodynamics. We must determine if a component is an active or a passive element. The second dimension is mathematical. We must identify whether the component reacts as a linear or nonlinear element. These definitions apply to all systems, from microscopic integrated circuits to massive municipal power grids. We are going to rigorously define these four distinct classifications. Correctly classifying a circuit is the mandatory first step that dictates exactly which mathematical toolsets an engineer is permitted to use for analysis. We begin with the thermodynamic baseline. The active or passive classification depends entirely on an element's ability to deliver power to the network. Active elements are defined as components capable of delivering continuous energy to other elements in a circuit. On a macroscopic scale, generators are a primary example. They convert mechanical work into a continuous electrical output. On a microscopic scale, standard voltage sources and current sources serve this same active function. Certain electronic devices, like transistors, are also classified as active. Though requiring an external power supply, they function as amplifiers, increasing a signal's energy level. Passive elements are components physically constrained to only absorb energy from the network. This absorbed energy is either dissipated as heat or stored temporarily within electric or magnetic fields. This identifies the three fundamental passive components: resistors, which dissipate heat, capacitors, which store energy in electric fields, and inductors, which store energy in magnetic fields. This strict definition explains why a transformer is a passive element. Although a transformer can step up voltage, the total power remains constant across the primary and secondary sides. Because it cannot amplify total power, it remains passive. At the system level, an active network contains at least one source of electromotive force, or EMF. A passive network contains none. This thermodynamic boundary reveals whether a network acts as the energy generator driving the system, or an energy sink shaping its response. Beyond thermodynamic energy, we must examine the stability of a component's mathematical parameters. A linear circuit is one whose parameters, resistance, inductance, and capacitance, remain constant regardless of the voltage or current applied. Linearity is diagnosed using a voltage ampere, or VI, characteristic graph. An element is linear if and only if its VI characteristic forms a straight line that passes exactly through the origin at 0, 0. To maintain this straight line, the element must satisfy two mathematical axioms. The first is homogeneity. Homogeneity is a strict scaling property. If the input current is multiplied by a constant K, the output voltage must scale by that exact same constant kV. An ideal resistor obeying Ohm's law is the standard example of homogeneity in practice. In this linear element, doubling the current doubles the voltage without altering the underlying resistance value. Homogeneity ensures predictability. Scaling a system's input proportionally scales its output without causing internal parameter shifts. The second mathematical axiom for linearity is additivity. Additivity requires that the response to a sum of inputs equals the sum of the responses to each input applied separately. If current I1 creates voltage V1 and current I2 creates voltage V2, then combining both currents must yield exactly V1 plus V2. Nonlinear elements are those that fail to obey either homogeneity or additivity. In these components, the physical parameters change as voltage or current fluctuates. On a VI graph, this results in a curved characteristic line rather than a straight diagonal. A standard light bulb is a common nonlinear component. As current increases, the filament heats up. This change in temperature increases the resistance, breaking the proportional scaling of a linear element. Diodes are also nonlinear, creating asymmetrical curves because their behavior changes based on the direction of current flow. This also applies to ideal voltage and current sources. Because their characteristic graphs do not pass through the origin, holding a constant voltage regardless of current, they are mathematically classified as nonlinear. When a circuit introduces a nonlinear component, proportional algebra is no longer sufficient, and analysis must rely on iterative calculus to find a solution. We can now synthesize these dimensions into a diagnostic taxonomy for any network. Standard resistors, capacitors, and inductors occupy the passive linear quadrant. The passive nonlinear quadrant contains diodes and light bulbs. The active nonlinear quadrant contains transistors. Analyzing an unknown circuit requires evaluating these two dimensions for every internal component. Establishing the thermodynamic state identifies where energy enters and leaves the system. Establishing the mathematical state determines if the system will scale predictably. Advanced network theorems, such as superposition or Thevenin's theorem, only function if the circuit is proven to be linear. Applying these theorems to a nonlinear component violates the core mathematical assumptions of the model, producing results that do not match the physical behavior of the circuit. Identifying these physical and mathematical boundaries dictates the selection of the correct engineering toolset, ensuring the resulting analysis is accurate and valid.
Let's study more, and like, share and subscribe for such more content, and comment something you want to learn.